Good afternoon. So I'm very happy to have Tim Davis as our speaker for today's seminar. Tim is a professor in computer science and engineering at Texas A&M University. And Tim is a leading expert in research for sparse matrix algorithms, and he's developed many algorithms and toolboxes that are widely used by academia, industry, as well as government labs. For example, the inverse function and matrix multiply in MATLAB use Tim's algorithms. Tim's received many awards for his contributions, including being inducted as a fellow of SIAM, ACM, and IEEE. And today he's going to tell us about his work on SuiteSparse GraphBLAS, which is a full implementation of the GraphBLAS standard for writing graph algorithms in the language of sparse linear algebra. So take it away, Tim.
Well, thank you, Julian. GraphBLAS. Well, this story starts long before my involvement. I've been doing mostly nothing for 30 years, sparse matrices being mostly nothing. And an expert on something knows mostly everything about their topic. So I know mostly everything about mostly nothing. I've been doing graph algorithms and sparse matrix algorithms for over 30 years now, but it was about 4 years ago now that the GraphBLAS spec started to come together as the group was getting together to decide, well, we want to write algorithms using graph algorithms, writing this in the language of linear algebra using sparse matrices over submarines. And oh, who's going to write it for us? Oh, Tim, would you write it? So, oh, that looks cool. So sure, I did. And so I'm coming in actually at the end of the whole GraphBLAS saga. Hopefully it's the end of the beginning, and then we have a new, and the work will go on, if we hope. But the end of a long process of defining what it means to do this work. It's been observed for a long time. In fact, my favorite algorithms book, Corman, Lieserson, and Rivest, right? It talks about doing adjacency matrices for graphs and matrix multiply and oh wait, we're going to take out do something different than the multiply with times and add and times operator. And so it's been observed for a long time. And so the idea of the GraphBLAS is to raise this up to a level of mathematical robustness and composability, and also construct a good C API, and then get somebody like me to write the reference implementation. So that's what I've done. So there's a whole host of people involved in this project. I'm just one small part here in the corner. That here at A&M, that's Reveille, that's our mascot. But people from all over supporting this and involved with this effort, and there's too many names to list. It's about 10 years ago that this book came out, algorithms in the language of linear algebra, which preceded the API, but laid out the algorithmic groundwork for the API. So that's a SIAM book by Jeremy Kepner and John Gilbert, edited by them, but by a host of people, many of whom are also on this slide. So what can you do with matrices? Well, just about anything, but what can you do with matrices for graph algorithms, and how can you write graph algorithms using and reasoning about them using linear algebra? So here's an example I like to use, which is breadth first search. And it turns out that the innermost kernel of a breadth first search is simply a matrix vector multiply. And wait, that will be slower. Well, no, it won't be. You'll see. So here's a traditional breadth first search, sequential. It's not a parallel written parallel. And so starting at node 4, here's the graph I'm doing a BFS on, and I want to find level 1, level 2, and I want to find the parent. So I want to build a tree where 4 discovered 1, and so 4 needs to be the parent of 1. 1 discovers 2, so 1 is the parent of 2 in the tree, and so on. So I'd like to build a BFS tree and also find the levels of this breadth first search. And this algorithm doesn't actually keep track of the levels, but while the queue, the set of nodes, is non-empty, grab a node from that set of nodes, and then for every outgoing edge, say if node 1, look to see I see two nodes. I see node 2 and node 4. Oh, but node 4, you've been seen before. So skip you, go to node 2. And hey, node 2, you've not been seen yet. So put you in the queue, set the parent of 2 to be 1, mark node 2 as seen, repeat. So that's the standard breadth first search. Now, if you write it this way, you'd have a hard time, unless you have a graph language, okay, that can parse this entire code, which is another powerful approach, of course. But if you just said, oh, let's call a library, let's write this code and then call a library routine for every line of code, a library function, well, there's no parallelism here that it can be expressed. It's too simple. But the observation is we can instead write it this way. This can all boil down into a matrix vector multiply. This right here, it doesn't look like it, but this entire body of work is a single matrix vector multiply followed by an assignment. So where does that happen? So what happens is this vector, this Q now becomes a sparse vector. And so that's this green vector over here. So this green vector here, suppose this has positions 1 and 3 present. The dots are 0. Well, I can't really say a 0. It's a thing not there. The thing not there in a sparse matrix, say in MATLAB, is 0. But it's 0 because they only use the conventional linear algebra semi-ring. This is not going to use that. So the dot just isn't there. It's like an edge in a graph that doesn't exist. Okay. So the vector is sparse. It has 2 entries, and the values of those entries are 4 because that's where it came from. 1 and 3, the parent is 4. So we put a 4 there. Now, I'd like to do a matrix vector multiply then of A transpose times Q. So the idea is you have this vector Q here, and you take an adjacency list of your graph, which is just a row of the matrix, and you ask of all those outgoing edges, which of them, let's see, doing the dot product, which of them, does any of them appear? So this is actually the dot product variant of the pull direction, not the push. Which of those would appear? If I looked across, I'm sorry, the incoming edges, I got it dyslexically backwards. If you look across the row at the incoming edges, so this A transposed, do I have a parent in the current frontier? And if so, I'm in. So row 2 would be in. So that's what's happening here. In row 2 gets in. So take this vector here, which is 1 dot 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 times this vector 4. So do this dot product, and it turns out there's only one place in the first position where an intersection is found between this entry here and this entry here. And the multiplication of 1 and 4 is 1. What? Yeah, trust me, I'll get there. Okay, it's going to be a 1. Why do I want a 1 there? I want a 1 there because I don't want to just use the conventional semi-ring. I want to use something else. I want to use something that tells me for row 2, where did you come from? And that's what I call the second I operator. So what's happening in this multiplication of row 2 with this green vector to get the red vector, second entry, I would like to combine these entries together and multiply them where they both appear. So there's only one place they both appear. The values are 1 and 4, but I don't want to just multiply them with a times operator. I want to do something different. I want to use what I call the second I multiplicative operator. This operator is doing this operation. It's the multiply of AI k times Q of k. But what I'd like to get is the position of this entry in the vector, which is the first position, which is the fact that my parent is node 1. That's who I see, where I see that I'm coming from. So I want a 1 there because I saw the intersection in the first position of this dot product. So in other words, AIK times QKJ, the second multiplicative operator, the second I operator, what I want it to produce is the row index K, which is I call it second I because it's the I, not the J, the row index of the second operand Q, which is the vector. So that multiplicative operator gives me the parent of node 2. At least there's one of them. Now, but what if you have more than one parent? I don't have this example in here, but what if there was also an edge from 3 to 2? Well, then there would be an entry here in this position, and there'd be two places where the dot product happens, and it's the job of the monoid, the additive operator, the summing ring, to sum those up. Well, I don't want to sum, they're indices. I want to pick one. Which one? The min, the max? Do I want the parent of one to be, I'm sorry, do I want the parent of 2 to be 1? I take the min. If you want the parent of 2 to be 3, take the max. But what if you don't care? So think of what a dot product matrix multiply is doing. The additive operator is summing up the numbers into one number. So the job of a monoid is to reduce a pile of numbers down to 1. The plus monoid sums them. The max monoid takes the max. The min monoid takes the min. But in this application here, any parent will do 1 or 3. So here you go. Pick a card, any card, and reduce this set of 2 numbers down to 1. There, your parent is 1. Okay. And if you run the code again, oh, your parent is 3 this time. And both results are valid. And so I can exploit this in the implementation. This is what I call the any monoid. It's a choice. If you have a set of numbers, say you've got a whole set of numbers, and the plus monoid would sum them up into one number. The max would take the king of spades. Whoops, that's the jack of hearts. The max would take the king of spades, and so on. The min would take, the ace of clubs, and so on. The any monoid would just go and say, well, there's your answer. Take it, the 3 of spades. That's your answer. It reduces a set down to one number. Pick one, any one, and the choice is arbitrary. It's kind of like the n of np. It's non-deterministic, but it's not randomized. I don't use randomization to get the answer. I just pick whatever I feel like to make it fast. So if it's parallel, and if I have a race condition, why not? Let it race. So this is the multiplication. Now, if you multiply these, this matrix times this vector together, you actually get more than just 2 and 6. There's position 2. There's another intersection that occurs in position 6, but also you get 4 as well. Oh, but wait. Node 4 has been seen before. I don't want node 4 to appear in my queue, my current frontier. It's my parent. It's already been seen. So throw that away. Throw it away. Well, many graph algorithms look like this. They have a tight innermost loop. And in that innermost loop, there's a little if condition that says, do this if the sum of the current edge plus this edge is less than the max of the edge, shortest path known so far, and so forth. Many graph algorithms have in their innermost loop an if statement. And what this does here, this is analogous. This is a mask. So if you don't have a parent, you go through the mask. So the mask says who gets to go through to the result and who doesn't. And in this case, it's the parent vector. And if the parent vector is empty in a position, then that's false. But we want to negate that so that if the statement is true, go through. So the negation, the complement of the parent, is the mask for this operation. And this entire thing is folded together into a single kernel in GraphBLAS. And the reason it's a single kernel is because the mask is very powerful, because I don't just do the matrix multiply and then when I'm done, pipe it through the mask. Sometimes I may choose to do that because I decide that's the simplest thing to do, because depending on the sparsity of the answers and the data structures I'm using and so forth, there are cases where that I actually decide to do that. But most of the time I use the mask to reduce the computation. I only compute where the mask will allow me to compute it. Otherwise I throw away the computation and won't go through the mask anyway. Okay, so once the current queue is computed, now the queue contains the parent node ID. So it contains, in this case, this entry would be blocked out, but the second element contains a 1 and the 6th element contains a 3, and that's the parent node coming from the second I multiplicative operator. And now I want to take that sparse vector Q and assign it into the parent and keep track of that. But I want to use Q as its own mask. I only want to put things into the parent that actually appear in the current frontier, because those are the ones that have been newly discovered that actually have a new parent. So add them to the loop. So it becomes a two calls to GraphBLAS to do a breadth first search in a loop. And it's kind of interesting. In this particular case, you'll see that the parent and Q, the vector Q, trade places. One is the result, one is the mask, and then it swaps itself. So that's breadth first search. And
so
you
question.
might, yes, please.
So I sort of understand, maybe I don't understand the semantics of the mask quite. I sort of understand the semantics, how I won't insert something that already was in Q, but I don't see how you avoided the double one getting inserted.
Which
in the red column,
the second one in position.
Yeah, you
4?
ended up with 2 1s, and you didn't want to put 2 1s into the resulting Q, right?
Right.
So you're overwriting Q, right?
That's a good point. It's what's happening actually in the code, and I didn't put this notation here, that there is a thing called a replace semantic being used. Okay, and in the actual matrix multiply here, which is this line of code, there's a little R there in this option, which is a specifies the replace option, which says as you write to the result. So what happens here, and I didn't add that here in this notation. There is, I could have put a little comma R there, but I didn't want to confuse it. But I see I've confused you by leaving it out. So this is a great question. So this matrix multiply occurs, and then the result is 1 and 1 and 3. Okay.
Yep.
Once that's computed, Q is cleared. Imagine. I mean, I don't compute it that way, but it's as if the replace semantic, which could be specified here to be more precise, says do this computation with Q and then clear Q and then write it through assign into the parent. So basically then the only thing in this A transpose times Q vector, which is the red vector here, the positions 2, 4, and 6. We have a vector with positions 2, 4, and 6. And at this point, nodes 1, 3, and 4 have a parent. And so 2, 4, and 6 is the vector Q. And I'm only going to be able to write it past the mask where the parent is not defined. The parent is not set for 2 and 6, but it is for 4. So 4 doesn't go through. So that's what's preventing the negation of the parent is what prevents this guy from going through. And is that more clear? Maybe
no,
not.
but I don't want to hold things up.
Okay. The one simple way to think about it is write this out in this assignment in a loop, where basically says test that condition, and if that condition is true, you can do the assignment. Otherwise, nothing happens; it gets blocked. That's another way to think about it.
You can even think about as element-wise multiply on the right-hand side.
You can think of it that way as well. You could write Q equals negation of parent dot star in MATLAB times this whole thing. Yes, you could think of it that way as well. It's like a dot star in MATLAB notation. MATLAB actually has the mask. You can do what's called logical. A mask in GraphBLAS is very much like logical indexing in MATLAB. There's a slight difference in what the input looks like. In GraphBLAS, it's an entire matrix. In GraphBLAS, in GraphBLAS, it's a matrix to matrix assignment. In MATLAB, you have to string it out into a big long vector, but that's a minor difference.
So, question is, why didn't you make it element-wise multiply? That would be a lot more linear algebra like.
Well, for a couple of reasons. First of all, what does it mean to do a multiply like a dot star? What's the operator? Well, okay, the operator would be the f of x equals x, y is just y. It's called the second operator. Yes, that could be done. The other reason, though, that it's useful to have it at raise it up even a little higher level than that, is that we'd like to use this mask in one of two ways with what are called the replace semantics, which is clear the thing and then write into it, or the merge semantics, which says if there's anything existing in the vector Q that is not obliterated or not written to, but already is there, it stays there.
So that would be plus equals. That would be something like
you
plus
would like
equals.
an accumulation. Yeah, exactly. But then what's the plus operator? By the time you start tossing in lots of different operators, it gets a little wonky. MATLAB has the mask. Why not? I mean, it's a once you get used to the hang of it, it makes sense. It's a conditional assignment basically. And then this is a conditional assignment that says assign to the parent only the values Q that appear. And where they don't appear, it's false. Only go through where you appear. And so this is a sparse vector assignment into say a dense vector. You have a parent, or into maybe a sparse vector. You've got a vector and you're only going to write into it. You're not going to delete anything. You're only going to write into things that exist. So it's using the vector as its own mask. So that's what this masking is doing. This mask is basically doing the same thing as this. If J is not seen, it means it doesn't yet have a parent. So if you do not yet have a parent, you go through. If you have a parent, this condition is false. And also you don't go through the assignment in the mask.
Okay, so I guess I understand that part, but I don't see why it gets rid of the second one.
Well, these two don't. The first and second one don't like merge together. They're not. They're not doing a dot product. They're not reducing those down to a single one. They're just three different numbers in positions 2, 4, and 6. They're all three treated. It's just a vector assignment. They're all going like this. And 2 and 4 get through, and 4 doesn't.
Okay, so just saying that 2 and 4 are both have a parent.
4 has a parent already. 2 and 6 don't. I'm sorry. Yeah, it's 2 and 6. Did I say 4?
Oh, it already had it.
Yeah, see, node 4 already has a parent itself.
Okay.
At this step in the computation. At this step in the computation, I don't show it here, but the parent vector has positions. It's a sparse vector. So the positions 1, 3, and 6. Oh, 1, 3, and 4. I'm sorry.
Yeah. So the problem is not that you had 2 1s.
Yes.
The problem was that 4 already had a parent, and you didn't want to give it a new parent.
Exactly.
Okay, got it. Thank you.
Yes, exactly. Yeah, the 1 and 1. It's not the fact that there's 2 1s. It's the fact that yes, exactly. I don't want to make, when I come down to here to node 4, I don't want suddenly make 1 its parent. I want to make 1 the parent of 2. I don't want to make 1 the parent of 4. 4 is the parent of 1. Sorry, and you're your own grandpa kind of thing. You can't, you wouldn't get a tree that way. Okay, so that's the breadth first search, and I'm already at 227. So let me jump ahead here. Here's the sort of things you can do with GraphBLAS. Imagine you take MATLAB and all the things you can do with the matrix in MATLAB. Now it's sparse. Oh, but it's any type you like. It's integer, complex, any scalar type you want to create even. And then star, what does that mean? Well, that's any semi-ring you like, and toss in the mask as well on everything, and you've got GraphBLAS. Okay. Things like matrix multiply, element-wise assignment. This is like the dot star in MATLAB. E-wise add is like the plus in MATLAB. Subscripting in both directions, assigning and extracting, computing operations on unary operations on elements of a matrix or vector, doing reductions to vector and scalar and so forth. So the key difference here between say this and MATLAB would be that you can redefine what matrix multiply means all you like. For example, any second I is good for breadth first search, min plus is good for a shortest path kind of algorithm, and many, many more. GraphBLAS algorithms are easy to write. We've got a MATLAB and Python interface, and yet we can get really good performance. In fact, we can beat the gap benchmark in some cases. which is a highly tuned specialized kernel that should always beat GraphBLAS, because I'm writing at a higher level API calling down to my kernels. The gap benchmark is just the kernels without all the layers of overhead of the nice, well-defined API at the top that provides this usability to an end user. That doesn't have to be there for a benchmark like the gap. So I should be able to, I can take my code and rip out all the beauty of the elegance and just give you the raw kernel and speed it up even further. But I'm not going to do that, because I want to be able to give this to the world and let the world use this API. One thing that's important also about GraphBLAS is I can be lazy. They can ask me to do something and say, oh, that's nice, thank you very much. Have you ever done this in MATLAB? Put a tight loop, create a sparse matrix with nothing in it, okay? And then sit in a type loop a million times and just stick one entry at a time. Boink, 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 boink. You'll be there about a week, okay? Because every time you insert, it's having to rebuild the entire sparse matrix, okay? It's order number of entries squared. Don't do that, okay? And the MATLAB lint checker will tell you don't do that. I can do that because you can tell me to do it and I'll say, oh, thank you very much. I'll pocket it. You tell me it again. Oh, thank you very much. I'll do it later. And I do this. So I don't have to create the result in the end. That's a powerful feature of GraphBLAS. The code appears in many commercial places, Redis Graph in particular, Linux distros, Python, and many more. And I'll show you one more that's kind of fun. Here's some other algorithms in GraphBLAS. PageRank is really simple because it's just a matrix vector multiply, right? But I use what I call the plus second semi-ring. Second says the second operator, think of times, f of xy equals x times y, right? What if x is always 1? And if it's not there, you don't do the multiply. If it's a sparse multiply, you don't do it. So whenever you apply a multiplicative operator and your matrix A is spones of A in MATLAB, it's all either not there or equal to 1, and then multiply that by, say, a vector. Well, it's just 1 times the value in the vector, or you don't use the operator. So the result is 1 times y. Well, then it's just y. So just pick y. F of xy equals y is the second operator, and then it can be agnostic about the data in the matrix. You can take a matrix with edge weights in it, with entries in it, and say, I just want to look at the values. Well, I'm sorry, where the values are, not what the values are. And so that's what's happening here with the plus second semi-ring. It's looking at the structure of the graph of the matrix, where the edges are, and ignoring the edge weights. Here's triangle counting, K-truss. This sparse deep neural network algorithm, my final code in GraphBLAS looks almost like the baseline in MATLAB, but it's 100 times faster. And it took me 20 minutes to write the C code to compute the sparse deep neural network. And it compiled and it ran and it gave me 100-fold speed up on the first time I compiled the code. It was that simple. Now, I wrote GraphBLAS, so I know what I'm doing, right? No, I'm not expecting everyone to get it that simple, that fast, but it was crazy fast for me to write the code. And so hopefully it's not too slower for others who haven't written GraphBLAS. So GraphBLAS is an implementation, SuiteSparse GraphBLAS is an implementation of the GraphBLAS API, and it doesn't have even breadth first search. That's where LAGraph comes in. This is a collection of algorithms that we're developing to sit upon top of GraphBLAS. This is a work in progress, very much a work in progress. But the features of SuiteSparse GraphBLAS, it has, in particular, these matrix and vector objects in GraphBLAS are opaque. Unlike, for instance, in MATLAB, you can actually go into the internals of a MATLAB sparse matrix. You're not allowed to do that in GraphBLAS. And that gives me advantages, because what if I haven't actually done the work yet? I'm being lazy. You've just asked me to do stuff and I'll do it for you. Trust me. And if you ask me to do something else and I can say, hey, I can do them both together way faster than I can do just the 2 things separately, I'll do that. But then you can't look inside my matrix. Just give me query functions and I'll give you the result that you want. So to do this, I store the matrix internally in 8 different formats. The complete Cartesian product of store it by row, store it by column, and I've got 4 data structures: hypersparse, sparse, bitmap, and full. I can just have it like a MATLAB full matrix. And I've got thousands of built-in semi-rings and operators. You name the type, I can do it. Those are just the built-in ones. And you can build arbitrary defined types and operators. I've got one example where the scalar is a 4x4 matrix and a 64 character long string, just for fun. It's fully parallel, but not yet distributed. It's OpenMP. We're working on a GPU code in progress. I exploit this non-blocking mode in 3 different ways. I have this pending update idea called a pending tuple. If you ask me to insert an entry into the matrix, I say, oh, that's very nice, thank you, and I'll pocket it. I'll stick it in an unordered list, and I'll stick it in later in bulk. A zombie is just the opposite. A zombie, I call it a zombie because it's dead, but it's still in the data structure. I mark it for deletion. It's a pending delete. And so, and it's a zombie because you can still tell it looks like it used to be a human, because I don't just delete the entry, I flag it for deletion. And I know what it's like. I got a tombstone in it. I know what that entry is. If it needs to come back to life again, I can bring it back to life. Or if I want to do a binary search in an adjacency list across and I deleted something, well, that's awkward. You hit a hole. Well, no, I want to hit a gravestone with a name on it so I can continue to do the breadth first search. So it's in that sense, I use the word zombie because you can still see that it used to be a human. And I also have a thing called the lazy sort. A lot of my algorithms, the adjacency lists have to be sorted in ascending order of node ID, and they don't work well. Like I might want to do a binary search, so I keep them sorted to make that my life easier. But a lot of algorithms like to produce a graph, a matrix where they aren't sorted. So that's not a valid MATLAB sparse matrix. It's not for me a valid graph for me, not a valid GraphBLAS sparse matrix. But some of my algorithms are tolerant of that as input. So I have a flag there that says, well, yeah, I'm not quite finished this, but here, try it. If you can use it, great. And then I don't sort it. And sometimes I can be so lazy, I don't sort at all. What if I construct a graph and I don't sort it, and then I come back and I never have to sort it and I delete it? Well, then it's gone. And I already said it's widely used. So here's some of the internal guts of what goes inside. And this is the parallel matrix multiply. There's multiple versions of this. I've got a mask dot product, which is, there's a tick there. Now pretend these matrices are all stored by column. If they're stored by row, then it'd actually be AB transpose, but it's MATLAB notation so far. So let's pretend they're stored by column. So this is the dot product. You're going to multiply a bunch of rows times a bunch of columns, and it's masked. Dot products in general are really bad for sparse matrices, but it's masked. So I only have to compute it where the mask is true. Or I can do unmasked dot products. Then I've got what I call a Saxby style, where you're summing up vectors. Okay. And this kind of algorithm requires workspace. Gustafson's methods uses a size n workspace, if you n by n matrices, for a gather scatter. Okay, that doesn't scale well to lots of threads. So if there's too many threads, I'll use different kinds of tasks. In fact, what I do is the first thing I do when I have A times B, I look at these two matrices and decide how much work do I have to do, and where is all the tasks going to be, and which tasks are going to do what, and I'll choose up to 4 different kinds of tasks, even for a single matrix multiply. Some will be coarse. A coarse task has the ownership of a whole column of the output, the C matrix. A fine task collaborates with a team on a single vector of the output. So there's coarse and fine. And then there's another distinction between Gustafson and hash. Gustafson has a size n workspace available to it. And so the hash function is identity. Just if you want the third entry, stick it in array position 3. Gather, scatter, really simple. But that can be too big. And so we just make it smaller and use a hash instead. So that's the hash tasks. They're a little more complicated, but they do basically the same thing. This is a fairly big piece of code. It's just the matrix multiply is about 10K lines of code just to do these A times B things. But I want to show you kind of the thing that has to go on under the hood to make this happen with the mask. Okay, so I'm exploiting the mask during the computation to reduce the work and decide who goes through and who doesn't. Now, that's easy to do in the coarse task because you just own the whole column. You just stick it in and you don't have any other threads to worry about. If you've other threads, they're worrying about, they're computing other columns of the output, and you own this part. But what if you're a team of threads computing the same thing, and you may have collisions? You might have atomic, you have to deal with atomics. this is a little teeny finite state machine then that exists for every possible position in the result. Every entry in the Gustafson table has a hash function, a hash finite state machine like this one. So it starts out here. Initial state of the mask the finite state machine is 0. And the first thing I do if the mask is present is I scatter the mask into the workspace. So now the vector is either 0 or 1. Then in the second pass, when I'm doing the numerical work, I use this finite state machine with a lock. So if it's true, if it's 1, I'll assign it to 3 and then spin. If I'm the one who did the lock, I get the 3. It's a compare and swap on this value. And then I can change the entry and nobody else can touch it. And then to unlock it, I don't want to set it back to 1 because that means it hasn't been seen. If I unlock it and it becomes a 2, then the entry is seen, and we're setting it back, it becomes 3. So what this looks like, and I have to watch my time, 2:40. It looks like this. This is just one piece, and I've simplified this a little bit. This assumes that the times operator is the little asterisk in C. Okay, it doesn't have to be. So what is this code doing? This code is one of a team of tasks that are computing a single matrix, single entry single column, the jth column of the C matrix. The mask is negated and it has already been scattered into the array. In other words, we've already done this. We've got 0s and 1s in this Gustafson workspace. Okay. So this is this little finite state machine that I have to then implement. And let me put this over here. And so what I do then, maybe I should make this smaller so you can see it at the same time. Okay, so I come down here and I'm going through every vector, every thread, I'm sorry, has a collection of entries in B that's responsible for. And for those, these are, if you will, the assigned nodes to this thread. And then this is iterating across the adjacency list of that node. Grab an outgoing edge, if you will, entry in a matrix, you're doing, or in the matrix multiply, grab its value, and then, well, if this is the any monoid, pick a card, any card, okay, whoever gets in last wins. So basically I read the flag to say, well, do you exist or not? Are you allowed to be written to? If you're allowed to be written to, then flag it as having been written to, because I have to keep track of who's there and who's not, and set the value. So this is what's happening in the breadth first search. Check a condition, set the thing to say you've been assigned, and keep track of who assigned, what the assigned value was. Otherwise, it's a little more complicated. And this is the case where you have to run the for all other monoids, like the regular. If I'm doing the plus times semi-ring, then I would come down here and do all this, and all this would take part. Basically, I grab the entry, so I read the entry. It's 0, 1, 2, or 3. Well, if it's a 2, that's cool. I don't have to change the state. I know it's been modified. I can just do a plus equals. Okay. Then if it's locked, I kick out. I say, well, I've looked at it already and it's a 1. The mask says I can't write to it because the mask is complemented. Then I said, well, now it's not set to true. Now I have to be careful. Now I have to lock the entry. This is the compare and swap. So this is the case here where I'm spinning. I'm going to write a 3 into there and hope to get out a 0. A 1 or a 2, a 0 or a 2 is what I'll get out. I won't get a 1 because I've already checked that. So we're writing a 3, and I'll pull out of it a 0, 2, or a 3. If it's a 3, I spin. If it's a 2, okay. Come down here, and it's an update. If it's a 0, this is new. I need to write it fresh. It's a fresh entry. And then when I'm done writing it, set it back to 2 and continue. Now this looks complicated, okay? But think about what happens, well, the any monoid, it's even simpler. Throw all this away and just do this. That's crazy simple. But say the add monoid, the regular conventional plus times, this looks complicated. The crazy thing is, though, is that this really only has to happen once, unless there's a race condition and two threads come in here and both think they're new, but one's not. Mostly what's going to happen is right here. One thread will come in here and say, you are in, and here's your value. Boom, assign the first entry. So you're doing a plus, you're summing up. There's the first entry. Okay, you're in. The next thread that comes along is going to see, oh, somebody's in, and here's my value, plus equals, boom. That's that simple. So most of the work is spent right there, where just use a simple OpenMP atomic. So this looks complicated, but it's actually quite fast, because most of the time you're in this finite state machine, it doesn't move. It just sits there in state 2, and you just see it's, oh yeah, it's a 2 and we're done. Now, caveat, if this is a user-defined monoid, there is no OpenMP atomic update. If you take this plus equals to say, call some function funky f of x, y that I have no idea what it's doing, well, you can't do that atomically. So this whole thing can't be done. Instead, I have to have a little critical section. I have to lock the thing all the time. So in a user-defined monoid with user-defined operators, this is the standard update. And so it's going to be slower. And also basically any monoid that doesn't have an OpenMP equivalent would come here as well. So that is what's happening inside all of these different sorts of, and I'm going to watch the time, 2:45. This is, let me jump over parallel assignment. Oh, I hate to do this. It's really cool. Well, let me say one thing. I'm going to run out of time. No, I'll jump. Okay, here's some outcome. Here's some results. How well does it work? Well, here's some comparisons with MATLAB. Same syntax. I have a MATLAB interface that's object-oriented overloaded. You can write A times B, and A and B are GraphBLAS matrices, and you get C, and it just happens to be faster. And I'm beating myself here because I wrote that. I wrote in MATLAB Art 2018A, A star B is my sequential code I wrote about 15 years ago. And so it's a single threaded code, and I'm now 30 times faster on 20 cores with some faster, even single thread. And then I get all the parallelism. Thing it is though, MATLAB just has the plus time conventional summary ring. I've got thousands of summary rings I can compute, and plus masking and such. This in MATLAB, COIJ equals A, this does an assignment of an entire submatrix into a bigger matrix. Okay, very important operation in MATLAB. I can do the same thing, same syntax, just with more types. You want a sparse int8 matrix, you've got it. You can't do that in MATLAB. And it's up to 1,000 times faster than MATLAB. You cannot do this in MATLAB. You can't create a matrix this big. MATLAB complains because, well, but I can. In fact, this matrix of size 2 to the 60 by 2 to the 60 takes about 1 kilobyte of memory to store. It's proportional to the number of entries in the matrix, not the dimension plus the entries, which is what this is. The mask operation appears in, am I muted? No. The mask operation appears in MATLAB, and I have the same syntax, but you give MATLAB a big enough matrix, like maybe 10 million by 10 million with a million entries to assign, and you hit enter with this one line of code, and you come back after coffee, it's still running. You come back the next day, it's still running. You come back a week later, it's still running. If you do the same syntax with a GraphBLAS matrix, it takes 7 seconds. So I'm getting some parallel speed up. It's not all parallel. There's asymptotic performance there as well. So these are the performance gains I'm getting versus MATLAB. A caveat though, I mean, this is an older version of MATLAB. You know, I really need to upgrade. So let's upgrade, okay, to 2021A, which just came out in 2 weeks ago. And now oh, dang it. I'm just as fast as MATLAB. What do you know? Oh yeah, I wrote that. So MATLAB just adopted GraphBLAS as its sparse matrix multiply. So that's a kind of like, if you can't beat them, join them. Now we're all the same code. And so this is where it's fun to see a competitor reach your level of performance, because now you are your own Anyway, so I wrote that. And so these other times haven't changed yet. And I can't say anything about the future of MATLAB. I'm not authorized to do that. You know, I don't want to give away any secrets of theirs, but you know, it's if this is the kind of performance you could see, then, you know, you can use your imagination as to what could happen. Okay, so that's exciting. That just came out 2 weeks ago. That MATLAB is now, the MathWorks is now using GraphBLAS, SuiteSparse GraphBLAS to do its matrix multiply, and just the semi-ring plus times and plus times float and plus times double and plus times double complex. 2 semi-rings out of thousands, but you know, maybe they'll expand. It's also in RedisGraph. This is a commercial graph database, which is getting some very nice performance. The engine inside this is all of GraphBLAS. And the RedisGraph came out in November 2018. This was just a year and a half after I even started writing SuiteSparse GraphBLAS. And this is with a single thread. They're competing very well against a parallel graph database called TigerGraph. Comparable performance to a parallel graph database. And now in April of 2020, they released a version of RedisGraph with GraphBLAS 3, which is using parallelism about 5 times faster than the old one. And then version 2, the sequential one. And now the new breadth first search is faster still. So here's also some other award. This is a Bluer research. It got Redis Labs got an award for RedisGraph for RedisGraph for seeing significant maturing in this application just in the last few years. So we have a Python interface. I think I'm going to have to skip over, but it's beautiful. The MATLAB interface is beautiful. You get very simple codes. But let me show you some performance results. So this is comparing against the GAP benchmark by Scott Beamer, which I have to say I've learned tremendous amount by reading his code and understanding, like this idea of the any monoid. Okay, if you read his code, I'm trying to understand why is his code so fast, and I'm looking at that. It's got a benign race condition in there. He's doing a compare and swap, and it's the last man wins, or person, last one in wins. Okay. Well, and how can I express that in a linear algebraic way? What is it that's happening to say last one wins? What is that doing? That's take a card, any card. Pick one. I don't care which one you get. That's your answer. Your node has any parent, any valid parent becomes the parent of that node, any valid parent. And so that's where the anti-monoid came from, by understanding his breadth first search. The BFS I have, you might think, well, gee, I'm using matrices. Aren't matrices costly? And in fact, if you read Corman, Leaserson, and Rivas, you'll see this statement in here. Now he's talking about a dense matrix. He says that the adjacency matrix of a graph requires order n squared memory, independent of the number of edges in the graph. Well, he doesn't clarify there that he's thinking about a dense matrix. This is not a dense matrix. All of this work I'm doing, this matrix vector multiply, it doesn't take time proportional to any dimension of the matrix even. It's not even order n. It could take order 1 time to do matrix vector multiply. Okay. It's proportional to the work involved, just as the BFS is. So this is a work efficient algorithm, but I'm a factor of 2 slower. And there's 2 reasons for this. One reason is that GraphBLAS is not yet fusing those last 2 operations. There's that matrix vector multiply and then the assign. If I could fuse those together into a single operation, I would be faster. I could skip some work. And the GAP benchmark is written with 32-bit integer indices, and I've got 64 bits because I want to handle bigger graphs. So I count this as a win, especially considering if you look at the readability of the code. This is code a mere mortal could write. Now, internally, no. The GraphBLAS itself internally is very hard to implement, but it's the API at the top that is meant to be simple. This is exciting.
Does your implementation use the direction optimization in BFS?
Oh, yes, it does. Yes. Let me show it to you. Yeah, I can show it to you too here. And I'll show you how simple it is. In fact, that's the breadth first search that I'm going to, here it is. If I'm doing push-pull optimization, what if I just did a push? I want to check from switching from push to pull. So if I've done any pull at all, just ask if the frontier is growing. But if it's in the general case, I want to get all the degrees of the nodes in the current frontier. So that's an assignment statement through the mask. W of Q equals the degree. And then I want to sum those up and get a number. And that's actually the flop count of this following matrix vector multiply, which I also would compute internally, ironically enough, because I want to decide what parallelism to do. But that tells me how many edges I will explore. And so I keep track of how many edges are unexplored. This is the same heuristic that Scott Beamer has in his code, just with different alphas and betas. I have mine up here. They're slightly tuned, differently because of different characteristics of our algorithms. This is the same heuristic as he has, just that it's using linear algebra to sum it up. Then here's the push and here's the pull. And a push is Q transpose A, and a push is A transpose Q. It's linear algebra. Do you want A B times B or B transpose A transpose quantity transpose? It's the same thing. One's a push, one's a pull.
For the pull version, how do you express the fact that you don't necessarily have to go through all your incoming edges? If you found a parent already, you can isolate.
Well, there's two things.
Okay. First
of all, there's a mask. The mask is the parent. I'm only looking for only considering undiscovered nodes.
Right.
Okay. Then this is a dot product based algorithm. Okay. So the vector Q is stored as a bitmap. I've already set that here. If you're pushing, I want Q to be sparse. If I'm pulling, I want Q to be bitmap. So I convert it here if need be. So now Q is bitmap, which Scott does as well in his kernel. So now I've got a Q as a bitmap vector, and A transpose is stored by row. And so I'm going to walk across that row, and it's a dot product between a sparse vector and a dense vector. And all I have to do is, and this is a bitmap vector, so it could be sparse. All I got to do is walk through until I find an intersection. So it's like a short circuit of a logical OR. You stop the moment you find a true. That's what I do here. So since it's any parent, I'll stop at the first parent I find. I won't find all of them. Like if it's the max monoid, find the biggest numbered node to be your parent, or smallest number min. No, stop when you find one. Anyone, doesn't matter, pick it. So that's deterministic. This is a deterministic choice. This would be the push. This would use that find hash table, and that would be a non-deterministic choice. And it's only non-deterministic because of the benign race condition.
Yeah.
That's the push, that's the pull. Okay. And then there's the assignment. Now, here's the cool thing. Between the centrality, the gap, I'm actually now beating the gap benchmark by up to 50%. He's taking 50% more time than I am. It's like, how can that be? This is a highly tuned kernel. This is like competing with a drag strip racer with a Lego car. Okay, it's Legos because it's just plug and play, stick it together, and then it beat the drag strip racer. How can that be? I'll show you how it can be. And I'll show you how beautiful the code is. It's incredible. You have to see this code. Well, that's just all comments. Okay. Between the centrality. So what the between the centrality is doing, it's asking from a set of source nodes, it's like a bulk breadth first search. It's doing a breadth first search, and it's counting how many paths go through, shortest paths go through each node, short in terms of number of edges. And then it has to do a backward pass to sum up those path counts to determine then the final centrality. And the centrality score then is, for all these source nodes, 4 of them, let's say, as an approximation, how many shortest paths go through every other node in the graph from those 4 source nodes to other nodes. So that's what's being computed, and it's 2 passes. There's a forward pass that looks just like a bulk BFS, and there's a backward pass that walks across the same set of frontiers and sums up the result. Okay, Scott Beamer has essentially 4 matrix vector multiplies in a loop. He computes, it's a sum of 4 results. So he just does one node at a time because it's too hard to do matrix matrix. Well, I've got matrix matrix. So I'm doing a single matrix matrix. He's doing 4 matrix vector multiplies. That's one reason why I'm faster. The other reason why I'm faster, he doesn't have push-pull optimization in his between the centrality. In GraphBLAS, it was so simple. It took me half an hour when I realized, oh wait, I could do this. I'll show you what it looks like. There it is. It's the same thing as the BFS. If you want to do a pull, it's the frontier times A transposed transpose. So I pass in the matrix transposed and then transpose it with the descriptor to say, please transpose this, which I don't actually transpose. I just compute with the effect of the transpose, or multiply by A. So do you want to multiply by A transpose transpose or multiply by A? It's the same effect. But internally, it's going to walk the matrix in a different way. And one's going to be a pull and one's going to be a push if the matrix is stored by row. If the matrix is stored by column, then actually these two things are flipped. But I'm assuming here we're storing by row. That's push-pull optimization in GraphBLAS. It's 2 lines, 4 lines of code. And it's fairly complex to do in Scott Beamer's code. So maybe he hasn't done it yet because it's complicated and it's not there. Well, this is push-pull between the centrality. This is push only between the centrality, basically. And that's why I'm getting a factor of 50% faster. And then the push, the backward pass looks the same, and it also has its push-pull optimization. Very simple test. So I just do an E-wise multiply. So this is the operation, divide by the current set of paths, number of paths, and then walk backwards from each set of frontier. And here I've got a mask I have to keep track of the frontier at every stage and then walk back and use those frontiers. It's too complicated of an algorithm to describe in every detail, but that's the entire algorithm down to there. It's simple it's almost like a MATLAB algorithm, almost like a Python level. There's no loops in here except the looping across every frontier level. Okay, large bulk operations. And again, on the back, do you want to multiply it by A transpose or by A transpose? Take your pick. It's the same thing. One's pre-transposed, one's transposed with the descriptor. One's the pull, one's the push. And that's what gives me this. So that's why this is in green. I'm actually beating the gap benchmark. My Lego car is beating the drag strip racer. Okay, so that's exciting. This is a factor of 2 slower, but I kind of count this as a win, not a win, it's a tie, because the algorithm is far simpler to write. So a mere mortal could write this, this code that I showed you. It's 3:01, so I better be wrapping up. Okay, I've got red here because I'm not always doing well. I've got some work to do here. For instance, a single source shortest path, I'm a factor of like 3 or 4 away from the gap. So I'm not always faster, and in fact, I'm rarely faster. But PageRank, it's just the same performance practically within 2 seconds, 10% difference. So this is the same performance because it's internally, it's the same algorithm. Okay, so let me sum up. Non-blocking mode, I have to skip over. So there's this whole question of and I don't want to call it I don't know what word I want to use, but 2 camps, right? There's the matrix camp and a vertex-centered camp. Do you like to think in terms of nodes and edges? Do you like to think in terms of linear algebra on adjacency matrices? And I say yes, both. Why not? It's not an either-or kind of question. GraphBLAS is here, and not everything can be as easily expressed in matrices as you can with node and edge stuff. There are some things like that I don't know yet how to do. And there's a lot of good libraries out there. I mean, Graphit, for example, there's a lot of good libraries that can do this stuff over here. Well, GraphBLAS has a constant time, it's like a move constructor, a constant time import expert. I can give you my whole matrix and say, there, it's your adjacency matrix, have fun. And when you're done with it, give it back and I'll keep going with it. So we can just hand it off to each other with no extra memory cost and no copy cost at all. So in summary, some strengths and weaknesses of the GraphBLAS approach. I think a strength is that it's like the triply nested matrix multiply. You don't like to write that. You want to like A times B. well, there's a lot of loops in a graph algorithm. You don't have to write those. Hoist it up to a higher level, like a MATLAB style level. You can avoid those loops and write it more expressively in linear algebra. And you can reason about it, like the push-pull optimization. You want to multiply by A or A transpose. That's linear algebra. And then one line, one expression, and you have it. It's a very simple high-level API. A lot of good scope for bulk operations, for parallelism in the implementation. Typically, the algorithms are simple, and most parallel algorithms most parallel graph algorithms can be expressed, I'm finding, in linear algebra. Most, anyway, not all. The non-blocking mode is very powerful. I can fuse kernels together and skip some intermediate results, which I'm exploiting more and more as time goes on. And I've got some asynchronous features that I can exploit with the NA monoid. And Python is no loss of performance. And MATLAB, you can lose a little performance using GraphBLAS because a MATLAB function is not supposed to modify its inputs. It can't, but I want to. And there's some cases where I make a tiny change to a matrix and give it back to you. That's instant. But in MATLAB, I have to make a copy of the thing, which is unfortunate. And it's got parallel performance that can rival and even beat, in this case, the gap benchmark. In 3 of those results out of 30 of the gap benchmarks, I can actually beat the gap on 3 problems. Limitations. Well, the strength is we avoid this. The limitation is you don't do this. You don't have that kind of expression of a graph algorithm of walking across the nodes and edges, which for some algorithms that's natural. But these 2 approaches can work side by side with import export. Some algorithms are hard to express. Depth first search, I wouldn't want to try it. Limitations in the implementation, I'm only doing some exploitation of this lazy mode of computing. And some fully asynchronous algorithms are really hard to express. For example, PageRank with Gauss-Seidel, where you update the vector and use it as you're updating it. GraphBLAS doesn't allow that. So it's just a limitation so much for the API. Maybe it'd be possible to extend the API because, I mean, Gauss-Seidel is, after all, a matrix expression, matrix idea. So these are matrices. So maybe you can do that. So anyway, that's GraphBLAS. And if you have any other questions, I'd be happy to entertain them. Thank you for your attention.
Yeah, thanks so much, Tim. So there was a question in the chat.
So I did not see it.
Oh, I can read it off. So the question is from Rakib Islam, and is there any particular reason for the huge performance gap between GapBS and yours for the road graph?
Oh, right. I skipped over that. I didn't mean to. Right here, for instance, this one?
Yeah.
Yes. So there's a couple things that are happening here. I've improved this a little bit. I know how to cut this down to 3 seconds, from 3 down to 1 second. I can cut it down. So I'm only 4 times slower than the road graph. The reason is the road graph has a very high diameter. It's otherwise a very sparse graph. It has a diameter of over 7,000. And so I'm doing 7,000 iterations, calling GraphBLAS twice. And then I've got things like memory allocation so I used to anyway so I had 100,000 mallocs. That was slow. So I improved that a little bit. I have a memory pool now, so that went away. But I still have a lot of very small operations to do. And when I do that, I have to use, when I do my matrix vector multiply here, I don't have a size n workspace lying around that I can stick my result in. The gap does. And the reason the gap does, so I have to use the hash method, hashing. I have to use hashing on a small workspace. But the gap doesn't. It's like, well, wait, it's the BFS. Why is that so different? It's different because the gap benchmark has been able to fuse together intrinsically. We're going back to this one here. These 2 operations, Q and parent and parent and Q. Okay. What Scott can do is parent is a bit vector, is a full vector, and he can, as he's writing into the frontier and noticing that, oh, this is a node that doesn't have a parent, he also does this. So he's modifying his mask He's using the mask as workspace and modifying it as he goes. So he can fuse these together, which if you're doing just a tiny, tiny bit of work, he just has a few simple gather scatter. There's no hashing he needs to do to have a small workspace. I don't have, when I'm doing this, I can't change the parent. Parent's a read-only object. And I don't know that this is coming. I could know, but I don't. If this happens, so the parent is a read-only mask, I can't change it. I can't use it as a workspace. Instead, I have to create myself a little tiny hash workspace and stick a few operations in there and then stick them in the result. And the hash method, hashing is slower than a gather scatter. And the work is tiny, and I have, I'm checking my inputs for, is it a valid input matrix, and doing all these other checks. There's just, and 7,000 iterations of this tiny loop. So it's difficult. Now, if I exploit fusion and then you say, okay, where is it? So those are the two reasons why. Now I wrote a new matrix vector multiply. Where is it? Here we go. So here's the matrix vector multiply, and then here's the assignment. He's got those fused together. I could too. I could notice one and say, oh, thank you very much, I'll do that later. And then not do the work until you actually come to here. Do both of them together. I can do that. The GraphBLAS API allows me to do that. I don't yet exploit that yet because that's a lot of work. Just do in general. It's a lot of machinery under the hood to make that happen. It is feasible. I know how to do it. I don't yet have the guts to write the code. So those are the several reasons why it's slower. Now, having said that, I did try to write a matrix vector multiply, which keeps workspace lying around that's all zero, that I can just pick up for free, use, clear, and put back. Okay. If I do that, I speed up the code like by a factor of maybe a little over 2. So I get a little bit of improvement here in the result. I get down to maybe 1.5 or 2 seconds here. So I can make this, so now I'm only 10 times slower instead of 15 times slower. But it's tough. I don't know if I'll ever reach this level. And it's even worse here. The sad thing about that extra new version of matrix vector multiply, though, is that when I tried it here, it actually made it worse. So I was kind of disappointed about that. So I chucked it. I'm not using that code anymore. I was hoping to make Road better with this one as well, with that same approach, but it didn't work out. So yeah, that's a significant difference. That's a factor of 20. Yeah, I guess it's just don't do road graphs. So good question.
Thank you. Does anyone else have any questions?
Yeah, Julian, I'll ask a question.
Yeah.
So thanks, Tim, for the great talk, and thanks for addressing both the successes and the limitations that you perceive in this library-based approach right now. I guess I was wondering if you could talk about what kind of future directions you're most excited about next for GraphBLAS, and what kind of graph algorithms you're interested in looking at in the near-term future.
Okay, great question. So the near-term future of the SuiteSparse GraphBLAS is GPU acceleration for one. And I was trying to make some new matrix methods to make this road graph faster. That didn't work out. Those are some of the near-term things. I want to, the other longer-term goal, I want to have some GPU acceleration going on with this. Under the transparent, you just say, here, do this matrix operation, and if it's big enough, it goes on the GPU. And then it makes it a lot faster without you having to know that you've got to, you have a GPU, but you don't have to write any CUDA calls. We'll do that all for you. So and you get the kind of performance even at the Python level. So that would be exciting if we could get that. And I'm working closely with NVIDIA on that, Joe Eaton in particular at NVIDIA, to make that happen. So that we've got working. I would, in longer term, there is there's the package called ComBLAS by Iden and John Gilbert and others, that those kinds of ideas could work together into a distributed memory GraphBLAS. So we could distribute this graph across a larger set of nodes. That's more work. I have a MATLAB interface. I need to speed it up parts of it, but it's in pretty good shape. I'd like a Julia interface. We have a Python one that's in good shape, 2 Python interfaces that are in good shape, that are working well. But there's no there's a draft Julia interface that needs some work that I want to look at. And then Fusion. What I really want is a JIT. I want to be able to spit out a file. See, this is not the code I write. This is not the code I write. I edited this to simplify it because this is a particular monoid. To make this code fast, I have to generate 1,000 copies of this code, each with a different operator there. Okay. And then I don't want to do that a billion times. So on the GPU, we're going to use a JITifier. We're not going to pre-compile a billion possible kernels. That's ridiculous. I could pre-compile 1,500 of them for matrix vector matrix multiply. That's already too many. I want to be able to, from my C code, take in your operation and spit out another C file, call the compiler, compile it, run it, and you're good. And then the next time, well, it's already there, so you're done. So you don't have to do all that but once. I'd really like a JIT. But it's not very portable across Windows. It's got to work on Windows and Linux and Mac and everything. And how do you write that kind of portable? Anyway, so that's the other thing I'm trying to do. What else? Oh, what kind? You also asked what kind of graph algorithms I'd like to look at. Oh, well, I mean, we're looking at better methods for connected components and graph clustering and community detection, maximal matching, K-core. Well, that's the LAGraph effort, which is a whole group of us all of us are trying to come up with good graph algorithms. And we're also open to contributions too, to the LAGraph effort. Toss in an algorithm. And so there's a lot of work that needs to go on there. And there's a feedback between the final algorithm and into GraphBLAS itself, and even to the API. For example, I could not make this. The breadth first search 4 years ago in GraphBLAS was probably 500 times slower than it is today. Parallel, yes, but between all these different operators I've added the any-monoid, the bitmap, the second die operator. Those are all additions to GraphBLAS. Now the bitmap is my choice internally because it's an opaque object. You don't care how I store my matrix. It's my matrix. It's what's yours, but I'll store it for you. But the any function, f of x y equals x or y, I pick, you don't. That's weird. That's not in the spec. I added it, and I added it by studying Scott Beamer's code, thinking, how does this get to be so fast? Oh, look, hey, that's a benign race condition. Could I do that? Yeah, I could do that. That's a monoid. Scott doesn't call it that, but why not? The math works. So
it sounds really exciting. So thanks for
this
pointing these out.
Cool feedback between the very high level graph algorithms into GraphBLAS to the API and back again. So it's a fun experiment. We're just trying to see how far can we push this idea, basically. And
we found this kind of in our work too. You implement a bunch of different algorithms, and you can't help but notice the commonalities amongst them. And this ends up giving you, simpler interfaces that can express all of them, and also make the implementations higher performance.
Yeah. I mean, we don't want users to have to write this kind of code. That's ridiculous. No one should write that kind of code. Well, me. Okay. I mean, but there is a lot of commonality. I mean, this push-pull idea. Well, there's push-pull in between the centrality. And it's so beautiful. It's so simple. I mean, Scott doesn't have it in his code. Now he'll probably go add it. Don't tell him, okay? Because it's so easy to express. That's the beauty of the API and the language. Since it's at a high bulk level, you can explore new algorithms. And oh yeah, that works, cool. And then if you really want it still faster, okay, go write the C++ code itself to make it go faster still, right? In the end, GraphBLAS will never win any performance contest, except when it comes up with a new algorithm that was hard to express, like this one. But I mean, I could take this algorithm and rip out my API and be faster still. And that would be, say, the next version of the gap benchmark. Then I can't beat that because you've got all those other assumptions. If you have full control of the entire algorithm, you can do any kind of level of fusion of these operations you like. You don't have to let some oracle decide on what can get fused to what. You can exploit all these things intimately, but at this level, it's hard to do. So a standalone, I mean, a high performance specialized kernel should be faster than GraphBLAS.
Yeah, I have a related question is, do you plan to support dynamic updates to graphs in SuiteBLAS?
That's a great question. Right now, the dynamic update I have is with this lazy mode, zombies and pending updates. So I have pending deletions, I call zombies, and pending updates, which are insertions that I just don't do yet. So if you have a bunch of those that come in incrementally, and they can actually occur not just in the assignment, but any place, in fact, anywhere there's a mask. Say I have a big matrix and a very, very sparse mask and a big A times B and a tiny, tiny mask, and just 5 entries go through. I don't want to stick those 5 entries into this matrix. It's got 1 billion values in it. I'll pocket it. They become pending tuples and do it later. And so these pending tuples and zombies occur everywhere in all of GraphBLAS. That's the only point right now where I'm doing this dynamic graph idea. I don't have a solution to the problem where you make a tiny change in the graph and then you want to run a whole graph analytic on it. Make another tiny change and then do something with the entire graph, or make another tiny change. Because if you make a tiny change in another tiny change, another tiny change, another tiny change, I can do that very efficiently. I'm lazy. I'll do them all at once at the end. But the moment you say, oh, multiply or transpose or whatever, then I have to say, oh, wait. Let me clean it up, So in that sense, changing a single entry, changing it, well, I can change an entry, but not the structure. If you change the structure of the graph and then ask for something like, what's the second level BFS from there or whatever, wait, hold on, I got to build you your graph. And so, yeah, that's another thing. Actually, I just had a conversation today about with one of my customers about they need dynamic graphs, more dynamic than what I give them. And yeah, so they need it.
Great.
Which means I'm more motivated to do it.
Right. Great, thank you. Any other questions?
Yeah, the BLAS has a operation, the triangular solve. Is there a space for that in the GraphBLAS?
I have thought about that. I mean, there are, you have to go one step above a semi-ring to solve a linear system. Is it a ring or is it a group?
It should be a field.
A field. That's the word I was looking for. A field. Yeah. So you could imagine a field, and then AX equals B, solve a linear system. I've done that for 30 years and do that over a field. Sure. Why not? I don't see why it can't. Triangular solve, QR factorization, LU factorization, Cholesky, you name it. Why not? So yeah, I think it should. Now, I don't yet have a graph algorithm that needs it, unless you want to do like cryptography or whatnot, but then that's not a graph algorithm, right? I mean, who needs to do like solve AX equals B over the Galois field or something like that? Okay. You could do that cryptography, I guess. I'm not sure where else that kind of thing comes up. But that would be a very nice direction of GraphBLAS to go in, I think. But I don't have that yet. I have solvers, right? I don't have a solver here. I've got solvers. I could add them to GraphBLAS and just tell me what ops you want to do. What do you want to do instead of a divide, or instead of a multiply or a subtract? Tell me. And what are your data types? Tell me, and I'll do it.
Yeah, I guess the question was whether there were any graph algorithms that would want that.
Yeah, at the moment, I don't have any. So I'm not in a big race to put them in, like the triangular solve, for instance. There are some things with like the Fiedler vector, but I'm writing a Fiedler's vector algorithm, but I'm using preconditioned conjugate gradient on the Laplacian, and I don't need a direct solver for that. I could use a direct solver. I'm actually using an iterative one, which, if you know me, that's a sacrilege. I'm a direct matrix. I'm a direct factorization guy. I do direct methods. I don't do iterative methods, but for that one, I'm doing an iterative solver. So yeah, that would be one place, maybe, you know, shift and invert kind of thing to compute an eigenvector. And a Fiedler vector, if you're wanting to know what that's kind of, think of wobbling a graph and then cut it where it's not wobbling. And that's a nice way to cut a graph in half. That's the Fiedler vector. And you need to solve an eigenvector problem. And for that, some eigensolvers need to use a direct linear system, a list system solve, AX equals B. And there would be a place where it could be used. I'm sure there's others, but they're just not like in my face. Oh, we have to do this. We need a solver. We need a linear system solver. We don't have that yet. So
thanks. I'll be on the lookout.
But yeah, if you see something, hey, we really need to solve a sparse Galois field 2 problem here. Oh, okay, let's talk about it. What would that look like to put a solver inside GraphBLAS? Cool. That would be cool.
Great, thank you. Any last questions from anyone else? All right, it doesn't seem like there are any other questions. Thanks again for the great talk. Let's give Tim a round of applause virtually.
Thank you very much. It was a pleasure. Unfortunately, we can't go out and have a cup of coffee or have a beer, you know, but whatever.
Yeah, hopefully we can do this sometime again after the pandemic. We can all go out. Yeah, great. Yeah, it's very interesting talk, and I look forward to seeing more of the work on SuiteSparse.
All right. Well, thank you again, everybody. And if anybody has any further questions you come up with later, let me know, and we can pop on a Zoom chat and talk.
Great. Sounds good. All right. Thank you, Tim. And take care. Bye.